So, hi, I'm Celeste Padilla. I'm Chief Engineers for the Emergency Response Unit. Thanks for everyone for coming. I forgot my timer. Cool. So our table of contents will first go over the mission profile and the communications, then hop into the requirements. Going forward into the design candidates, we'll take a look at the landing mechanism, retrieval mechanism, and the drivetrain. Then taking a look at our weight and power analysis and our hardware and software. So our mission profile first begins being deployed by MAC and then switching into autonomous mode to navigate our way to the hiker. Then manually preparing and loading the hiker, then switching to autonomous to navigate back to navigating to the evacuation point, switching back into manual for the transfer of the hiker to MEA and navigating our way to HQ. During all that, we will be sending communications to GCS that you can see down below. Now we move on to the first requirement. The vehicle shall be able to survive an in-flight drop from the multi-role aircraft. Derived from there, the vehicle shall interface with MAC. It shall be able to slow down during the descent and shall be able to operate after X feet drop. The vehicle shall be able to withstand XG loads upon impact and detect the correct landing orientation. That orientation being wheels on the ground. Next, we move on to ERU2. The vehicle shall be able to drive up a 30-grade hill at 1.5 miles per hour while fully loaded. The vehicle shall have a minimum X milliamp hours drive to drive up the hill, and the vehicle shall be able to produce a minimum speed of 1.5 miles per hour. The motor shall be able to output a minimum and maximum X feet times pounds amount of torque to drive up the hill. The vehicle shall have the ability to travel up the hill with an X pounds of weight. Moving on to ERU3, the vehicle shall be capable of autonomous waypoint navigation. Derived from there, we have the vehicle shall receive the target coordinates from GCS, and the vehicle shall gather sensor feedback from the environment to transmit it back to GCS. The vehicle shall be able to detect and transmit its current location and orientation, and the vehicle shall support autonomous navigation real-time processing. ERU3, the vehicle should detect and avoid obstacles such as rocks and trees along its path. Derived from there, the vehicle shall be able to detect obstacles of length, width, and height of inches, and the vehicle shall detect the obstacles within X amount of feet and should autonomously navigate to avoid these obstacles. And the vehicle shall have a minimum response time of X seconds and also have sensors to detect these obstacles. ERU5, the vehicle shall be controlled via GCS. So the vehicle shall be able to transmit the feed wirelessly to GCS, and the vehicle shall maintain a signal at a maximum of X feet. The vehicle shall send a minimum and maximum X bit rate to establish continuous communication with X milliseconds of latency. The vehicle shall be able to switch between autonomous and manual mode. Checking along, ERU6, the vehicle shall transmit the video feed to GCS during manual navigation. So the vehicle shall be able to transmit this video feed wirelessly to GCS, and the vehicle shall have a minimum of one camera to capture this video feed. ERU7, the vehicle shall be capable of preparing an immobilized hiker for transportation. Derived from there, we have the vehicle shall be capable of preparing a hiker of a maximum 0.4 pounds and shall not further harm the hiker. and shall be able to transport this hiker to MEA. And it shall be secure, the hiker shall be securely hauled during the transportation, and the hiker shall be laying flat on the ground to be rescued. ERU 8, the vehicle shall have a range of 1,800 feet fully loaded. Derived from there, we have the vehicle shall have a minimum power X milliamp hour to travel the required distance of 1,800 feet with the hiker. The battery shall provide to be determined amount of milliamp hours to the entire system through the mission. So our ERU 9, the vehicle shall have a maximum dimension of 12 by 7 by 7 inches. ERU 10, the vehicle shall have a maximum weight of 8.5 pounds unloaded. ERU 11, the vehicle shall have all core electronic components on the removable tray. And ERU 11, the vehicle shall pose a removable electronics. I just realized that that's derived from there. Removable electronics tray that will securely for the duration of the vehicle. And the vehicle components shall not block or disturb the communication signals. ERU 12, the vehicle shall be capable of transporting a hiker of a minimum of 4 inches. ERU 13, the vehicle shall be able to operate in weather conditions consisting to sunny, overcast, no rain to light rain of 0.2 inches per hour. And ERU 13.1 is the vehicle shall have an IP rating of no less than 54. And ERU 14, the vehicle shall transmit a health and status information to GCS at a rate of no less than 1 hertz. Now I will pass it on to the mechanical lead, Corey.
Hello, my name is Corey Gao. I'm the UGV mechanical lead, and now I'll be going over ERU Mechanical's subsystem architectures, which includes our landing mechanism, retrieval mechanism, and drivetrain candidates. We will now begin with our landing mechanism candidates. Last year, we considered a single parachute versus a sacrificial platform and decided on the single parachute. This year, we were building on top of this comparison by looking at the single parachute versus multiple parachutes. Through our research and trade matrices, the single parachute offers advantages that include a lesser likelihood of entanglement and an easier deployment compared to the multiple parachute option, which has a higher chance of entanglement and costs more while offering the same performance as a single parachute. After research and conducting our trade matrix, we decided that the single parachute would still be the best choice, and now we will move on to our retrieval mechanisms. Our 3 retrieval mechanism candidates are as follows: the conveyor, the rescue net, and finally the scooper. Beginning with the conveyor, it is a belt conveyor retrieval system that positions the hiker on a separate detachable stretcher that gets taken away by the MEA. Some of the concerns with this design is that it has low precision, low security, and concerns with long hair and loose clothing getting caught. Moving on to our second candidate, the rescue net in the center, which manipulates a net under the hiker in a 180-degree sweeping motion and lifts the hiker with ease. This design minimizes pinch points, has good security, and a reliable retrieval. In addition, this design has simple detachment methods where the net can be pulled off the grooved rods or gently placed down and driven away from. The final feature of this design is what we call the turret arm system. The system includes a turret-style swivel like on a tank and arms that gives us the vertical motion we need. The turret arm system has also been adapted for our final candidate, the scooper. This design scoops the hiker by pushing the thin platform under the hiker and then securing and protecting the hiker with the closure of the protective cover. This design has a more complex detachment method than that of the rescue net. The off-center placement of the mechanism allows for more room for components such as sensors and cameras. And the stretcher platform can be detached for retrieval by the MEA. That's a typo, I'm gonna have to fix that. But continuing, through our trade matrices, we decided that the rescue net is the best candidate, and we will now move on to our drivetrain candidates. Okay, shown here are our drivetrain candidates. First, single/dual Ackermann turning, and second, differential turning. Single and dual Ackermann turning allows us to effectively implement suspension, which provides terrain absorption and a better ride quality. This drivetrain also allows for high maneuverability when turning, and the implementation of two-wheel drive and four-wheel drive. Our next candidate, which is the differential, also known as tank turning. This design allows for a zero turn radius by pivoting around a point midway between the drive wheels. It is mechanically simpler than the Ackermann, reduces drivetrain losses, and is easily capable of two-wheel and four-wheel drive. We chose the single Ackermann turning after conducting our trade matrices as our architecture for this year. Now I'll pass on to Daniel Mankir to discuss electrical.
Daniel?
Sorry, I forgot I was muted. Hi, my name is Daniel Menker, and I am the electrical lead of the UGV vehicle. And I'm here to demonstrate the weight and power analysis of the electronics of the vehicle. So here we can see we have both the weight and power analysis of the electronics components that'll be on the vehicle. As a disclaimer, these parts may or may not be included in the final product of our vehicle, but are provided to show a rough estimate of what the electronics on the final vehicle will look like. The only parts that aren't included in these calculations are the camera to send video feed to ground control station, 2 dual servo motor controllers, a single servo motor controller, the battery to power these components, and 4 other servo motors, as we are still looking into components to fulfill these roles. As we are still analyzing the benefits of using either 1 DigiKey motor or 2 DigiKey motors to rotate the vehicle's wheels, we have 4 graphs here for 2 situations, using 1 motor to rotate the wheels and using 2 motors to rotate the wheels. Each situation has its own pie graph for weight analysis and power analysis. For weight analysis, our electronics end up being around 0.91 pounds for 1 motor and 1.15 pounds for 2 motors. In both situations, much of our weight is taken up by the DigiKey motors and the ultrasonic sensor that we plan on using. We plan on using 3 ultrasonic sensors so that we can accurately detect and avoid obstacles in the vehicle's way, which is why the ultrasonic sensor category for the electronics weight is so large. With this information, it's much easier to calculate how close we are to the maximum weight of 8.5 pounds. For power analysis, our electronics ends up consuming around 1,430 milliamp hours for 1 motor and around 2,097 milliamp hours for 2 motors, where the DigiKey motors end up consuming the most current out of all the components. This information, looking for a battery is simple, as we just need to find a battery that has more than either 1,430 milliamp hours or 2,097 milliamp hours, depending on if we use 1 or 2 motors. Moving on to the next slide, we have the printed circuit board that we plan on using for the ERU, also known as a PCB. As a disclaimer, again, this PCB design and the components on the PCB may or may not be included in the final product of our vehicle, but is provided to show how we plan on powering and or communicating with other components on the vehicle. Currently, we have 8 Molexes on the board, which are the white pieces located near the edge of the board that act as an input for the battery and as outputs for different voltages for the other components that will be on the vehicle. Our 1 input Molex is labeled as U1 on the PCB, and the rest of the Molexes are outputs for their respective voltages. To get these different voltages that we need for these components, we need a voltage converter, which converts higher voltages to lower voltages reliably. Currently, we have 2 voltage converters on the board, a 3.3 voltage converter labeled as U2 and a 5-volt converter labeled as U3. The wires that connect these components together are the lines you see on the board. These wires need to be a certain thickness so that they can withstand the current going through them at all points in time. Otherwise, they can burn out, which disconnects the component from the voltage converter. After doing some calculations, we found that a wire size of 10 mils or 0.1 of an inch is enough to withstand all the current going through the board. With that being said, I will hand it off to Louis Nguyen to present the software side of our vehicle.
Hello, my name is Louis Nguyen. I am the UGV software lead, and I'll be talking about our research into utilizing a robot operating system as the communication layer between a simulator robot and our hardware robot, and between our data analysis software MATLAB and then the modeling environment Simulink. So ROS will use messages to exchange information between each other, and because of this, we're allowed to use, and since it's an open source framework, we can utilize other people's ROS nodes that they've already built for different robots and test it on our current robot. And because of that, we can explore the different robot interfaces that's already been developed, and we can develop our own algorithms towards the research and control precision for our purposes, whether it's for our drive system or it's for the pickup system. And we refine that soon in the simulation. So 3 different ways we can analyze this data is either first is by recording the data in the simulation and the hardware testing, and then importing that into MATLAB or Simulink, and then doing visual analysis through graphs and camera analysis. The second way is to do a live connection in the ROS network, and that way we can accurately send and change parameters in real time and observe how they affect our drive system or the pickup system and calculate which is the best method, which is the best parameters for so. And then our last method would be to generate prototype standalone nodes that don't utilize MATLAB, so where there's no dependency on the MATLAB and Simulink as a way to send data over, and it can be the final form of our autonomous system and deploy as an autonomous system on the simulation, and then eventually the real robot. Next slide, please. And so these are just some sort of all the different features that MATLAB can present. The most important ones that we want to focus on is the control systems one. We want to be able to allow control systems people to develop either multiple input, multiple output, or single input, single output controllers, and then utilize them for real accurate precision testing on drive systems for autonomy in that, and also the eventual idea of autonomy for pickup. And then eventually want to test this on our robot simulator Weebots, a 3D world with physics properties on it. We can test those controllers on it, develop the prototypes either through real connection or through importing data. And eventually, once we've kind of finalized that, we can generate our standalone ROS nodes. And then we don't need dependency on MATLAB or Simulink anymore to send data over to our simulators and robots. And eventually, if we want to go into it, we can use the MATLAB applications for image processing, image acquisition, and computer vision if we want to include more autonomy to our robot. And I'm going to pass it over to Mario, our embedded lead.
Hello, everybody. I'm Mario Molina, this year's embedded lead. As the UGV's embedded team, we're looking to create a control system for the ERU and all of its components. This control system will be an array of custom hardware descriptions, drivers, and C and C++ applications accumulated into a field programmable gate array, or FPGA. We'll also have a dual input system, which will allow us to offload component drivers that are ill-suited for FPGA implementation to a Raspberry Pi. This dual input system will run on a Linux operating system for both the Raspberry Pi and FPGA ARM processor. The diagram you see to your left shows a flowchart of creating a software-hardware concurrent design through pre-established intellectual properties, so think processors, and our software/hardware development, so think pulse width modulation modules. Of course, there are many steps to this process, as you can see, that deserve its own slideshow, but essentially we can harness the resourcefulness, the versatility, and the speed of an FPGA to drive our ERU components through this process, all while not reinventing the CPU. On to our next slide. I'd like to bring your attention to our first figure, figure A. This is most representative of the work we do in embedded, as we want our custom application programs to interact with C and C++ libraries and a custom-made device tree with our hardware descriptions in it, custom drivers, and of course, custom drivers in between. The other figures, figures B and C, are also attainable, but from different frames of reference. Potential challenges include limited thread count on the FPGA. FPGA implementation shouldn't be done for all components, as explained before. And of course, custom hardware takes time to create. And lastly, I want to bring up this last image is simply to illustrate how our custom hardware, so this blue and red image you see, can have custom hardware on its on top of it. So custom hardware on top of custom hardware. Connections, and then finally connections to pre-existing intellectual properties like a system communication bus or controllers. Overall, from the progress I've seen, I have high hopes and expectations for the embedded team, and certainly we can attain some form of FPGA implementation on this year's ERU. Thank you so much.
And now I'll discuss our path to PDR of finalizing our designs, beginning testing, completing and custom software drivers / hardware images for select FPGA driven components, dual input control systems fully planned, and our torque and distance analysis and our wire schematics. And with that, if anyone has any questions or comments, we can now open up the floor.
Damn, guys, you guys did a good job. Like I'm wholly impressed by the level of detail you guys had in your CAD designs. They looked really, really, really good. The level of work that your software and electrical and embedded teams have put in, that that was a lot. That was way more than we had in last year's, which is kind of what I was talking to MEA about. But if all of the design teams, MEA and you guys are putting this much effort into your hardware, electrical, and software this early on, like if you guys have the time, yeah, like I don't care if it hasn't been done in the past. I think it should stay in because both teams have done good work, and like the FPGA work you guys got a lot on your plate, Mario.
Oh yeah, definitely. But I actually am very happy with the team that I have this year. I'm very proud of them.
that I'm just
Yeah.
saying, I'm excited for it, but that's ambitious. You're basically saying like you're gonna build out a whole custom hardware network on an FPGA
Mhm.
fabric and then interlace that with an onboard processor.
Yeah.
I like it. It's ambitious.
Yeah, it's all about pre-planning. I feel making sure we decide what's attainable and what's a little too difficult to achieve the deadline. Like I mentioned. Yeah.
Yeah. All right. Fair enough. And then just again, being an electrical and computer background, I got to nerd out for a second before I go back to some other stuff. The decision to move to ROS, I'm sorry, I missed who presented the software slides, but why did you guys make the decision to pivot to ROS away from, so we've done Python and C in the past, and now you guys are going a completely different direction. Not that it's a bad one, just different.
The decision to move to ROS was a suggestion by Boscovich.
I knew it was freaking Bosco.
Yes.
I was watching those slides and I was like, it's got Bosco's fingerprints all over it.
Yeah, at the very least, if it doesn't like turn out the way we want to, we can use the ROS node generation and then just convert, because I know it converts into C++ nodes and also Python nodes, and then we can use that as an interface to build our custom code on. But basically, it's just kind of like the way we want to get really precise with our like autonomy, because we really want to try to dive into autonomy for pickup and other things, and we can't have that if the pickup system is not precise enough. That can affect the model we're picking up, the human, and we don't want any like bad things with that.
Okay. I like it. I mean, so I'm not going to be a lot of help to the software team this year because I have very limited experience with ROS. But so for everybody here right now, both schools, for the electrical and software teams, yeah, let's talk, because I'm trying to get you guys more mentors. We have a lot of flight and a lot of aero and mechanical people that have always been able to help out the project, but electrical and software hasn't been able to get as many mentors kind of in the pipeline. And like, I was not prepared to ask people about, finding someone who knows ROS. So let's definitely talk so I can figure out what support you guys need, and I can try to find the right people at Northrop to support you. And
Yeah,
that's
for
for
sure.
that's for all the electrical software and embedded teams on the call from both schools. Yeah, I want to make sure you guys have support. And yeah, I would have been, if it wasn't for today, I would have not known to say that you guys were using Ross in the materials I'm putting together to try to get mentors. So I'm glad that I now know that. So, okay. Let's back up for a second. So we can go through some of the notes that I have. So can you go back up to slide 4 real quick?
Yeah.
There was something. Oh yeah. Yeah, I would just reword some of this, and I don't know, check with faculty. I feel like ERU 1.01 could be a top level derived requirement that you're just saying that you have to interface with Mac. I don't know that directly, like, yeah, you have to survive the fall. That's true, but yeah, I don't know if that's necessarily derived. So you might want to double check that.
We ran through it with faculty before, and that's the first time we're hearing about.
If they're
but yeah.
happy with it, then don't worry about it.
Okay.
It just stuck out to me. So you guys have already gone through these recs with faculty?
With one of them, yes.
Okay. All
We
right.
had a content review on Thursday with Ben.
Okay. Okay, that jumped out at me, but if they think it's in the right place, then I'm not going to argue the case. Like, I don't have as much experience with requirements as they do. I work on a test set team, and so we deal with requirements a little bit differently than you would when you're dealing directly with a client. Okay, slide 5. Yeah, I think it was ERU. So the minimum speed of 1.5, that's just, I don't know. I feel like some of that's worded weirdly, but I won't get, we won't get bogged down in it. It was mainly the battery shall have maximum X milliamp hours to drive up the hill. I thought that was a strange requirement to have in there because milliamp hours generally refers to like your total operating capacity, which it's what you guys talk about later in your with 1800. Usually for something like this, you would just talk about power. So like I would talk to maybe Boscovich and Zeki about that requirement. Like electrical, jump in here with me if you have any comments, but like milliamp hours to go up a hill, it's not like you got to drive 45 minutes up a hill, you know, it's just you have to be able to navigate an incline essentially at that minimum speed. So and then yeah, ER 2.02 feels kind of redundant just because that's the requirement is you have to be able to go 1.5 miles per hour. Like it's already stated there. You know what I mean?
Yeah.
So I would talk to Bosco and Zeki about those two. Slide 6. Yeah, what does that mean? The vehicle shall gather sensor feedback from its environment and transmit to GCS.
So like the feedback that it'll get, whether it's like video feedback or another type of feedback, we'll just be able to transmit it.
But you know, there's no requirement like other than having to send a video during other than having to send a video feed during manual control, which should be, I think you have something in that section about sending a video. There's nothing in the requirements that require you to send back like information about your surroundings. You need to send where you're at and the status of the vehicle, but you don't need to send like if your LiDAR is popping off or something, you know what I mean?
Okay.
Like I again, that's just something I would double check because that feels like a scope creep. You know, you don't need to be sending back telemetry data. That's not in your mission statement. You're not scouting per se. You're trying to like you're not. It's like they build robots right to go into rooms and 3D map the room. In which case you're like either recording or sending back telemetry data and things like that. But in this case, You guys just have to execute the mission and then provide a video feed. And I'm pretty sure you have a requirement to send video data under your that top level requirement. So
Okay.
like, yeah, there's just no reason to impose extra bullshit to have to send over the network if you don't need to. So I would talk to Zeki and Bosco about it.
Jeff, if I can jump in here, I think
Yeah.
the reason for this requirement, I agree with you. We shouldn't have it say transmit to GCS, but I think it was kind of hinting that the vehicle shall have some type of sensor that can detect obstacles while performing autonomous navigation.
Right, but then that goes under but the thing, autonomous waypoint navigation and obstacle avoidance are separate. That's why they're two different top level requirements. So in order to execute autonomous waypoint navigation, you need to be able to receive coordinates, aim in a direction, and drive, and that's it. Like, you don't need to know anything about your surroundings to do that, right? Strictly speaking, that's why it's a separate requirement. So if you, and then in your guys' requirement for, that you should be able to do object avoidance, you have a bunch of stuff that says we're going to be able to detect objects and drive around them. So that's what I'm saying. With the way this requirement is worded, at worst it's scope creep and implies that you have to send telemetry back to GCS, which you don't, and at best it's redundant. So that's kind of what I was getting at.
Okay, that makes sense.
So I would kill it, but if you want to confirm with faculty first, because they do have more experience than me, like I'm not going to argue that point with them if they really think it should be there, but I would remove it if it was me. Slide 10. Hiker. So hiker lying flat on the ground shall be rescued. There's nothing in the RFP that says the hiker has to be flat. Doesn't say they can't be either, but there's no reason to put that limitation on yourself. Like, maybe I just don't feel like it needs to be there.
It's not more so like a limitation. It's more of just making sure the hiker will lay flat, because with our designs right now, it's the most easiest to get him well flat. So it kind of benefits us to have it there.
Okay. If you feel like it's more beneficial, then that's fine.
Yeah.
Yeah, that's all good. The vehicle shall not further harm the hiker. I like that requirement.
Yeah.
And then point 7.01 is coming from the top level system level requirement, right?
Yes, it is. I'll change that.
All right, cool. No, it's fine. I'm just saying, like, you might want to comment on that's because that's the requirement as the hiker is that size.
Yeah.
And if you also have the height requirement somewhere else, so you might want to tie those two requirements together.
Okay.
13, slide 13. The wind speed changed, so make sure you catch that change. At the system level, I updated the wind speed to 5 miles per hour. If I think because you guys derived ERU 13 yourselves, right? But
Yes.
you moved it in here. Yeah. So that top level requirement has changed. The wind speed's now 5 miles per hour because it would have been a nightmare for a helicopter or a quadcopter to try to operate in 15 mile per hour winds while picking something up. So we dropped the requirement. Slide 17. Yeah, this one you might want to break into 2 slides. It's just it's a lot of good information, but it's a little overwhelming. So I would just rethink how you're presenting this so that it's a little cleaner. It makes a little more sense. Again, it's good information, but there's just a lot of it on one slide, and it's just a lot to try to absorb as a viewer. Go back to the. Can we go back to the parachute slide real quick?
Yeah.
One more, or nope, too far.
Sorry, my keyboard got stuck.
Nah, it's okay.
And it's not going forward now. It's
so funny. There you go. Let's just stay in this view. That's fine. Yeah. So on your other ones, you have your candidate, and then it's sort of summation. On this one, you show a single parachute and a multi-parachute, but then you're just kind of generic. I don't know if you're kind of talking about advantages on one side and disadvantages on the other, but I'm not sure if those are, you know what I mean? Like, this feels different than the other slides.
Yeah, I see where you're coming from.
Yeah, so like if you're gonna, put your single parachute and then, as I mentioned with MEA, I think more like key attributes might be a good way to talk about it as opposed to advantages and disadvantages, and then just sum up each one, and then you can say which one that you're leaning towards and for what reason. You know what I mean?
Yeah, sounds good.
And you guys threw out a lot during your presentation, trade matrices. It's fine. That's great. If you've got them, fantastic. They don't need to be in the presentation, but if you're going to mention them, have them ready to pull up, whether they're in your
Supplemental
backup pack,
package.
your supplemental package, hopefully, but be ready to pull the trigger on those in case you're asked. Like, okay, well, you said you got a trade matrix, so you better show me. Like, I don't care. I'm not going to ask to see them, but Barnaby might.
Yeah, we were planning on adding them on the slide.
Let's see. Jump to slide 18 real quick. Yeah. Use a block diagram here. The PCB, it's not doing anything for you. Like you've got a couple of regulators on there, but like I would dump this and do a block diagram that shows kind of what you plan on using for your custom, like what are your inputs and outputs going to be of your custom PCB.
Okay.
Does that make sense?
Yeah, that makes sense. I'll get to work on that.
You don't have to do anything crazy complicated, but like just do a high level block diagram that shows what you're planning, right? So you got some power coming in one side, it's going to go into some regulators and whatever, step down converters, and then you've got power coming out the other side. You know what I mean?
Yeah, I have a block diagram for the electronics for this vehicle, but it was still in the works, so I didn't
Okay.
put it on the slide yet. Yeah.
Okay. Honestly, too, I mean, if you don't want to do the extra work right now, you probably don't even need to talk about it. You could just mention on your previous, like you might be able to mention somehow that you are going to be using, regulators to step down the 12-volt power to something that's usable by your Pi and your FPGA and all that stuff, right?
Mm.
Which, speaking of which, are the FPGAs 12-volt or 5-volt?
That's a good question.
It is a good
Mario,
question.
do you
And-
know?
All right, hold on.
Well,
Let me wait. Stop. Let me put a pin in it. If we get into the weeds, we're gonna be. This is what I was talking about, where the point of the presentation creeps a little bit because now I'm interested in this stuff. I want to talk about it, but I don't want to derail us. So, one thing that you guys will want to do, right, is you want to do analysis on all your components. So I know you have a top level analysis showing, and this applies for all the electrical teams if you're listening. I know you have a top level analysis showing, yes, we can pull. We're going to get batteries that will supply this amount of pull or supply this amount of current so that we can run everything. But your regulators have to be able to support your current load as well, right? And
yeah.
you need to be able to make sure that the 12-volt, like if your FPGA is 12 volts, right? Like the ones we use in our labs are 12 volts. If your FPGA is 12 volts and you're pulling, like, if you're hooking directly up to the battery, is that safe for the FPGA? Or are you going to have a separate converter to make sure that your current and power and everything is safe for the FPGA as well? Not, you know what I mean? And like, so you guys are going to want to do analysis on all your components to know what they require, exactly how much voltage they require, what the current that they require, current draw is, make sure that your regulators and all of that stuff can handle that. Because even if you have the right regulator, right, if you're pulling too much current, then you're gonna have a problem.
Okay.
Am I making sense?
Yeah. Yeah.
So that's just for all the electrical teams. Be ready for that. Like you're gonna want. You don't have to have that by this presentation. I'm not saying that you got to have all that ready in a week. That would be nuts. I'm saying that as you go forward, you want to look at every single electrical input and output you have and make sure it's all simpatico.
Okay, I got you. Thanks, Jeff.
Yep. I think that's all the notes that I had for you guys. Embedded electrical, you guys have a ton of good information on your slides. If you guys, for everybody involved, all of the presenters, you guys all did a good job. I would, if you have the time, you guys got to time it out and make sure and work with Lizette and Maria, or on the slow side, work with Teresa. Slow down and talk through this stuff when you have a lot of good information and give yourselves time to kind of speak on it, right? Like you do have to keep time in your head, but if you have it, slow down a little and really go over what you've got, because you guys have just an absolute ton of good information on some of these slides.
Got it. Yeah, at the moment we came out to 21 minutes. I think we're provided 30 minutes, so we might want to slow down. But yeah.
Yeah, you guys can slow down. You know, for all the teams, you especially, you know, all of you guys slow, and you guys so far have got more information on your slides than we had last year, which is not a bad thing. I keep saying, like, don't wait for Northrop, just go and you know, do the work and show the work that you've done and ask for feedback on it. So I think after seeing your guys' presentation, assuming that MAC is kind of MAC is kind of in the same place, that it makes sense to leave the electrical and software stuff in. Teresa, I don't know if you're still there, but since it looks like you guys are all kind of simpatico with each other in terms of like content, I think it's probably safe to just leave. Okay. Does anybody on ERU have any questions for me before we move on then?
Yeah, I had two questions. So, first one is I should just straight up remove the PCB slide and replace it with the block diagram, correct?
I would just kill it. I don't think you're that PCB is not doing anything for you. Like, people who know a little bit about PCB kind of know what's going on there, but at this stage, you're more important to show. I think it's more important for you to just show like a block diagram of what you think your electrical system is going to look like.
Okay.
Right. And if you want to make it specific to just what you've got to worry about from a regulator perspective, that's fine too. Right. So it's like, you know, we also we got a 12-volt battery on board to run the motors. We're going to be pulling power off of that to power everything else. And to do that, we're going to custom print a PCB that can do a bunch of power regulation for us. Show the block diagram there or something. If you want to talk to me about it in more detail after the call sometime this week, we can. I just don't think that was helping you at all.
Okay. Cool. And the other thing, a lot of what's it called? The units for current or power consumption are in milliamp hours. Do you think Northrop would prefer watt hours, or is milliamp hours fine, or do they just not care?
I don't think they'll care too much. As long as I would say that you all on all teams across both schools should be consistent. As long as you're all consistent, it's fine.
Okay.
Milliamp hours is what I think when I think in terms of capacity. Like, I know, you know, there's other ones out there, but milliamp hours is always the one that makes the most sense to me.
All right. Cool. And I'll coordinate with the other electrical engineers, make sure that we're all on the same page then.
Yeah, as long as you're all consistent, I don't think it'll be a problem.
Okay. Cool. Thank you.
Mhm.
That's all the questions I had.
Anybody else?
I was just wondering, like how long it might be till we can hear back from you about the mentors for Ross.
So for everybody on the call, I am doing I'm making a push so I work. Okay, let me back up for a second. For anyone who doesn't know me, I work at Northrop. I'm an electronics engineer. So I work with a lot of hardware and a lot of FPGA development. That's kind of my job right now. So I'm trying to pull from the people I work with to get hardware electrical and FPGA support. And then I'm trying to pull from the software people that are on a separate team, because I don't work directly with software, to get software support. So most likely these are going to be folks who don't have experience with NGCP specifically, but have the technical experience that's needed. So I'm putting together kind of a little one sheet, like recruitment slide to send out to both departments, hardware and software, to try and get, you know, 4 or 5 mentors to come in and help. I'm hoping to know in the next couple of weeks. It depends on how quickly people get back to me and how quickly I can kind of push that process along on top of my 40 to 50 hour work week. So I'm trying to balance things. In terms of Ross, I'm going to be completely honest. I have no clue if I'm going to be able to find someone that can help with that. Like, honestly, right now, I would lean on Bosco heavily, because Northrop, to my knowledge, at least the people in my sphere, Ross is not readily used. So on that specific point, I'm not sure from the Northrop end how much help I can get, but I believe Bosco has good experience with it. So you might have to lean on him a little more heavily right now.
All right, then. Thank you.
And for the record, for the mechanical and aero people, you were not left out. Nicole's got your back. Like there's a lot of mechanical and aero people that always support. For any of you who haven't presented, there's a lot of mechanical and aero people who support those presentations and who give feedback. So please, like my expertise, my background is computer engineering. So that's why I'm talking a lot about like that. Nicole couldn't be here today, but please don't think that you guys aren't getting support either. That's just, I don't know anything about that stuff. So I'm limited help in that regard.
Yeah, they're good, Jeff. They can hear it all from Barnaby.
Okay. I didn't want the other majors to feel like they were getting brushed over. That's not the case. That's just not my area. That's more Nicole's specialty.
No, it's fine. Electrical finally needs to be appreciated.
Yeah, it's been years, and electrical, like my first year on the project, electrical software and embedded was difficult to get support from Northrop. So I'm hoping now that I'm on the Northrop side and I'm still directly supporting the project that I can get more help. So we'll see what happens.
Awesome.
Can I go next?
Yeah.
All right, so I'm going to turn my video on because I want to be extra prepared. I'm not trying to flex. But yeah.
Just so I know, Marissa, how much time do you have? I want to make sure that